So welcome to Alum at Alma talk series. This is third talk in this series. Our today's speaker is Dr. Biswabandan Panda. He is a faculty member at the Computer Science and Engineering Department at IIT Bombay. He completed PhD from our department. His well-known microscopic contributions are the state-of-the-art high-performing cache compressors and multi-level hardware data prefetchers. He is one of the recipients of Qualcomm Faculty Award 2022 and Google India Research Award 2022. When I was for the faculty position, Vishwa was a PhD student, and he, along with Madhur, they took me for a dinner, and I think their feedback was instrumental in making sure that I didn't lose this job. So I owe a lot to Vishwa. Over to you, Vishwa.
Thanks, Rupesh. Just confirming again, you can hear me and see me.
I am able to hear you as well as see you. Yes.
Okay. Thanks. So yeah, thanks for this e-invitation, and it would have been better if it was not online, but nevertheless. And thanks for your kind words at the end. I still remember the dinner that we had sometime in 2013, if I'm not wrong. Okay, so I'll talk about microarchitecture, and I'm assuming the audience has UG, PG, and especially masters, MS, and PhD students. So it will be at a high level. If you don't understand all the things that I talk about in the next 1 hour, it's perfectly fine. The goal is to make you curious about some of the things that are happening at the microarchitecture side. Okay. So this will be our protocol for next 1 hour. We are already finished 180 seconds. So I will have 2 checkpoints where you can ask me questions because it's an online talk. We can't have a dialogue frequently. So I'll pause at slide number 35 and 67, and then we can take questions that time. So Rupesh talked about his story, but I thought it's a good opportunity to look back where I started my journey at ITM. So this was actually an email sent by Madhu sometime in 2009. With the possibility of an MS offer, and that's how it started. And then later I converted into a PhD program into 2012. And then thanks to the department website, it still has a name. So I just took a screenshot from the department website. Okay. So I used to work at the Rice Lab, but mostly I used to roam around Rice Lab and Pace Lab. These 2 labs are still there, I believe. And there used to be a department computing facility, DCF, that was the route between this Rice Lab and Pace Lab. So few more, stories or the old memories. So the first picture that you can see is with Ravindran, and then with my advisor Sankar. So I used to be a temporary member of their office BSB 349, so that's why I put it. And then there are some few other pictures during my MS and PhD days. You can see that the T-shirt remains the same over the years, and that's the first takeaway out of this talk, that you should maintain consistency, if not anything else. Okay, so I'll take 1 more minute to talk about some of the things that you may or may not know. So as I mentioned, I joined the MS in 2009 December, and 2 years into my MS, I was still fixing tools and simulators for doing architecture research. Ideas were getting scooped, and around January 2012, I think these progress meetings are still there at ITM. It used to be called as GTC. And suddenly the committee said, what exactly you have done in last 2 years? And my answer was nothing. I'm just trying to fix a simulator. So sometime around February 2012, I applied for a conversion from MS to PhD. The committee said, no, I think you should take some more time. I did another presentation. The committee again said no. And then finally the committee said, okay, go for it, but be careful. Okay. So finally I graduated. That's why I'm giving a talk as an alumni. But the real story is actually the ups and downs and not the straight line that you are seeing at the top. So honestly speaking, sometime around 2012, I was thinking whether I'll be able to get an MS degree, forget about PhD from IIT Madras. So thanks to CSE department for that. So after 2015, the ups and downs in research still it go on. It's not like it's end once you finish your PhD. So it's a daily affair, but now I'm kind of used to it. Okay. So with that, I will start the talk, and now it will be on microarchitecture and some of the things that we have done, my students and I have done in last few years. Okay. So before jumping into microarchitecture research, let's understand what exactly microarchitecture is. So if you can see the slides here, you'll be seeing a chip, which is, it can be a famous Intel chip or something like that. Uh, can you guys see it? I'm actually showing a Intel chip. Can someone say yes or no?
The chip is visible.
Sorry?
Yeah, it's visible.
Okay, okay, thanks. Yeah. So this is actually a processor where, where you run your program, the OS actually does all the job that it is supposed to do. And there is an interface through instruction set architecture, let's say x86, RISC, ARM, or whatever. But there are many things that are not exposed to the programmer. When I say programmer, it can be user, compiler, or the OS. And that's called the microarchitecture. They are the hidden hardware units which are sitting inside your processor, and their only goal is to improve performance. Okay. And then there are many such microarchitectural units, and they work day in day out to make sure your program runs fast. Okay. So with that, I'll jump into the microarchitecture research. So this is not something new. Microarchitecture research has been going on from last 30, 40 years. And there is a common myth, at least in academia, that microarchitecture research is dead. So I wrote a blog about microarchitecture research that appeared in ACM Cigar last year. Go and read about why it's not dead. But in the next 10 seconds, I will try to answer why it's not dead and why you should be excited about microarchitecture research. So this is a famous quote from Alan Kay. He's a Turing Award winner for many contributions, but he's known as the father of small handheld device. So he talks about people who are really serious about software, they should actually make their own hardware. But is this statement true, or this is just some academic statement that people give once in a while? Right? But if you look at the current world, the processor market is not driven by Intel, AMD, or IBM. That used to be 10, 20 years before. Now, in this slide, you can see all the big companies. In fact, all the software companies are here, like Google, Facebook, Amazon, Microsoft, NVIDIA, who is a company that is famous for GPUs. They are also jumping into CPUs. So, which means this field is actually not dead, and everyone is building their own processor. That means everyone is also curious about microarchitecture ideas for their own processors. Okay. So with that motivation, I will jump into the context of the talk. So for the next 45, 50 minutes, I'll assume that we are running programs on our CPUs. When I say programs, these are binaries along with the OS that runs, on an Intel server or on a mobile phone, right? And we'll try to improve performance of our applications that we are running on the CPUs. Okay, so let's run an application. So I know it's 2023. Everyone is talking about Chat GPT, but I don't have numbers for Chat GPT. So let's go for a simple application like web search, and let's run it with a recent Intel CPU. Let's say Intel Haswell, right? So this slide shows where exactly the runtime is actually bottlenecked. So the term bottleneck is actually a technical word that tells you what fraction of the time the CPU or the processor is actually not doing anything and waiting for some thing to happen, right? So if you pay attention here, you will find more than 50% of the time it's actually bottlenecked by two terms called backend memory and something called retiring. Okay, so this is pretty latest number. These are not like numbers which are 20, 30 years old. So let's understand what are these bottlenecks. So first of all, the backend memory. So on a processor, you will find multiple levels of cache, like three levels in general, L1, L2, and L3. And they are actually used to hide the DRAM latency. So DRAM is super costly. Okay. So the processor talks to memory for two things. One for the code, and the code is usually stored in the iCache, L1 iCache. And most of the applications you will find the code is actually fitting into your L1 iCache. The hit rate is almost 100%. So the problem is solved for most of the application, if not all. But then the backend comes into picture where the processor or the CPU actually asks for the data. So you run your program and the program demands data, and that data won't fit into your small L1, L2, or LLC cache, and you have to go to DRAM. And the DRAM is actually pretty costly, as you can see here. That the few cycles for L1 and then tens of cycles for L2, but beyond that it will be hundreds of cycles for accessing anything from the DRAM. Okay, so this is one of the bottleneck. The next bottleneck is actually called the retiring bottleneck. So here I'm jumping into out of order processor, where the processor actually looks for opportunity to execute instructions in an out of order way, not respecting the compiler order or the programmer order. So in this slide, you can see there are 5 instructions. Three of them, which are in red, they are memory operations. They will go to cache or memory. The other two are simple arithmetic operations. But the crux here is, even if instruction 2 and 5, which are arithmetic instructions, they are done with, let's say, 1 cycle or 2 cycles, they have to wait for the first instruction to get done, and then only they will be termed as completed. Okay, so this is needed to make sure that we respect the order which was generated by compiler, and then things like exception handling and other things will become easier. So no matter how aggressive our processor will be, at the end of the day we'll be using a structure called reorder buffer, which makes sure that all the instructions, the way they entered the processor pipeline, they should also exit the processor pipeline in the same order. So this creates another bottleneck, right? So even if you get a hit in the cache, it may happen that because of a long latency DRAM access, there will be instructions which are sitting in your processor just waiting for that response to get done. Okay. So these are the two bottlenecks, and we'll try to mitigate these bottlenecks in the next few minutes. Okay, so what will be the ideal solution? Impractical, but ideal solution, right? So the ideal solution will be if I can provide L1 cache hit rate of 100%. What I meant by that, every time the processor demands for data, my L1 cache will say, yes, I have the data, I have all the data that you need, and there's no need to go to DRAM, maybe after first few accesses, right? And how can you do it? Maybe you can come up with another microarchitecture called, let's say, Prefetcher, as the name suggests. You can fetch the data before time and put it into the L1 cache, so that in the future, when the processor demands for the data, it will get a hit. Okay, so far so good. So what will happen if we go for this ideal world, which is not practical, but still. So suddenly you will see that all the memory operations are just taking 5 cycles each, and the bottleneck that used to cause by the retiring operation is actually no more, and even the L1 cassette can actually get it. They can complete their pipeline operation in few cycles instead of hundreds of cycles. Okay. So at this moment, I will pause, and our goal is to solve these two problems: the retiring bottleneck and the memory footprint bottleneck. And we need to find out microarchitecture solutions. So again, microarchitecture solutions meaning you should not change your program, you should not change your operating system. Everything should be done inside the processor, so that the programmers should have the free lunch and still get performance improvement. Okay, so I have already talked about the structure called Prefetcher. Here I'm just showing a textbook kind of example where the structure Prefetcher sits beside a cache. It looks at all the requests sent by the processor. In this case, let's say the accesses are x, x plus 1, x plus 2. A simple Prefetcher will actually anticipate that, okay, in future, the processor may demand x plus 3. And it will actually go to DRAM, get the data for the address x plus 3, and if all goes well, in future, the processor will actually get a hit because the data for address x plus 3 is already there in the cache. So this is a simple speculation, prediction, or guessing mechanism where you are trying to predict the future accesses by looking at the past. Okay, now let's jump into the research trend. What exactly people have done in last 20, 30 years. If you look at the literature, you will find most of the prefetchers are actually designed for L2 cache, which is the mid-level cache, and not for L1 cache. Well, the issue is there are many challenges for building a L1 prefetcher because the L1 itself is a pretty tiny cache, and it was kind of a myth, or it was kind of a unquote quote and unquote uh, kind of message that you can't build a L1 prefetcher which can be high performing. Okay. So I'll stop for a few seconds here and then think about a bit of philosophy. So this is from my postdoc mentor, post PhD, when I was working with Andre. So his research philosophy was whenever when the community says, okay, we can't solve this problem anymore, it's done. You will start seeing, in the top conferences, flagship conferences, the number of papers in that topic is going down, right? So that's the best time to actually jump into it and make your mark, because people have given up, right? So but then you can say, what about impact, right? If you are solving something that people have solved for last 30 years, yeah, it has its own pros and cons. But if I look at from Indian academia perspective, especially Indian systems research community perspective, it's really hard to join the race that is created by the US grad schools. So my approach, at least from last 5 years, is you try to solve a problem that people have given up. It will take time, but it's worth it, and I will show you why it's worth it. Okay. So this is the question that I was asking along with a few of my students or interns sometime around 2018. And the question was, can we design a highly practical L1 prefetcher? Okay. And the answer that we got is actually no from both academia and industry. So the challenges were many, as I was talking about. The L1 cache itself is pretty small, so you can't put so much intelligence into your L1 prefetcher. It should be small also, and it should be agile, so that you will be able to do many things in a few number of cycles. Okay, there are many architectural issues that I don't want to jump into now, but take me for granted that there are tons of issues when you design a L1 prefetcher. That's why industry and academia, they were actually dealing with L2. But it also provides opportunity in the sense that L1 cache is the cache which is closer to the processor. So whatever programs that you have written, the memory accesses will be unfiltered if you look at the L1 cache and not at the L2 or L3, right? And the other benefit is if you put a prefetcher at L1, it will bring the data for all the three levels of cache, L3, L2, and L1, right? So it can do the job of L2 prefetcher that you have been proposing, and on top of that, it can bring data into the L1. So finally, we actually proposed a prefetcher sometime around 2019-20, which appeared in ISCA. And this work was actually done by a remote intern from BITS Planning. So I won't jump into this particular paper because I have presented this idea at IIT Madras sometime around 2019-20. So, but I will stop with a message that, if you're doing research, it may happen that most of the people are actually going in a particular direction, but it's really important that you should stick to your gut feeling and then dare to do something different. Okay. And so this is the impact that we created, the ISCA paper that I talked about. So these are the top high performing prefetchers, state of the art prefetchers. All are L2 level prefetchers. And the way to look at these numbers is there is a cost associated with these proposals in terms of storage. They are like 6 kb, 34 kb, 119 kb. And we propose something which is less than 1 kb, but it beats all the prefetchers in terms of performance. Okay. But then if you are working on something else where you get tons of performance improvement, let's say 2x, 10x, or 100x, you'll say, what exactly this big deal? This is just 2% improvement on top of existing state of the art. So just to give you a reality or the real picture in microarchitecture research, so if you are improving state of the art by 1% every year, that leads to a big difference in the final revenue of these microarchitecture companies. So these are some of the famous quotes in the community. Some of them are anonymous. Some of them are actually there on the Google, on the web. If you search it on Google, you will get it. But the takeaway message here is this 1% improvement matters. Okay. So I'll pause here as I have promised before I jump into the actual talk where I talk about some of the recent works. So any questions at this moment?
Vishwa, this is Naresh Swami here. Am I audible?
Yeah, sure. Yeah.
Hi. Hi. So this prefetching that you spoke about. So basically, the decision for prefetching will be made where? So would that be a separate coprocessor kind of a unit which is not using up the cycles of the CPU, or this would also be done by this prefetching would be done by the some electronics on the CPU itself?
Okay, yeah. So that's a good question. So it's not a co-processor. It's a simple microarchitecture unit. The way we have caches,
Okay.
you can say there is another small circuit which is actually doing the job of a prefetcher, right? So, but the crux here is this is a speculative technique. You know, the prefetcher is running on its own along with the CPU. It's not hampering the CPU performance when it is predicting something. Okay. So the point here is the CPU should not execute few instructions to do prefetching. That will become a software prefetching technique. Here, there is intelligence which is inbuilt into a hardware unit, which just observes the past accesses and then based on that it speculates.
So therefore, while designing a prefetcher, one can also take into account compiler optimizations which are done and so on. Is that correct?
Exactly. That's what I will show in one of the slides. Yes.
Okay, okay, thank you.
Yeah. Any more questions, or I will move on? Okay, so maybe at the end. So after that work, the community started looking at L1 prefetchers. Industry started funding me, and then we started asking, okay, what next? What should we do? So then we came into a problem which is pretty obvious, but no one was talking about this problem. It's the problem about energy. Okay, and what exactly is energy, I will talk about in a minute or two. So this is a work done by a MS student at IIT Kanpur when I was at IIT Kanpur. So currently the student is at EPFL doing her PhD. So we actually make a case that when you design prefetchers, you should not forget about the energy or power aspects of it, because modern day systems are really power hungry, and then it can actually lead to serious implications if you are dealing with data centers and then cloud servers. Okay, so this is a high level overview about energy, what exactly energy is. So the energy consumption part of any processor or any microarchitecture unit will be divided into two parts. One is static, one is dynamic. So dynamic is if you are doing some job, let's say the circuit is performing some task, so it will actually take some power, right? So that's the dynamic side of it. Static is even if you are not doing anything, the circuitry is still driving voltage and current, and that's why you are consuming power, right? So now the question is, when you are designing a prefetcher which is supposed to improve your performance, whether it improves your power budget, whether it actually does everything within the power budget that you have specified. Okay. So there are few more techniques that people have proposed in the last few years, which are highly sophisticated and pretty interesting if you want to understand. So there is a technique called power gating, which is used by all the modern processors. So the idea is if I'm getting my requests, which are getting satisfied at my L1 cache, so then what I can do is I can put my L2 cache at a lower voltage level so that it won't consume more static power. Okay, pretty neat and intuitive idea, works really well. But what happens if you turn on a prefetcher? Now prefetcher will actually start sending requests to L2 cache with the speculation that I need data for the future accesses, right? And with that, it may happen that you will actually end up, increasing the energy consumption. So when we started looking into this problem, first of all, we found that there is no tool that is available to do research which can give us faithful numbers. Okay, so we reached out to industry, various industries said yes, no, yes. So finally, it took around 10 months. Forget about research. This is just understanding what exactly is the problem, how big is this problem, right? It took 10 months for the student and me to get a yes from Intel Labs, thanks to Intel, by the way. And then after that, we started doing research on this topic. So again, I will give a message to most of the MS and PhD students that it may happen that things are not, moving, you are not progressing, all kinds of things come into mind. But it's really important to, hang in there and then persist. If you want to make a mark, eventually, that eventually is subjective. It can be few months and few years. Okay. So where was the problem? I said that in the presence of prefetchers, the energy may become a serious issue. And the problem was all these prefetchers that we have proposed or the community has proposed, they are not 100% accurate, which means whatever I'm predicting now, it doesn't mean that those addresses will be used by the processor, because this is based on some intelligence, some heuristics. It's not a sacrosanct prefetcher. Okay. So what's the solution then? Well, I started with the notion of retiring bottleneck, where I said that, there are some loads which will actually go to DRAM. They will get a miss in L1, L2, and L3 or LLC, and they will take so much cycles, because of which the processor has to stall its execution for hundreds of cycles. So instead of prefetching all the instructions or prefetching for all the instructions, why not prefetch only for those instructions that delay retiring instructions, right? So that will be my small subset now. And if that's the case, I will actually start issuing less number of prefetch, and I will prefetch judiciously only for the prefetch, only for the loads which will actually make an impact at the end of the day. Okay, so this is our first observation. If you look at this plot, these are for various benchmarks from cloud server workloads, and then various spec CPU benchmarks. The crux here is there are two things. One is called load IPs, meaning load instructions, and there is something called critical instructions. So if you look at the numbers which are in red, they are pretty few in number, like tens, sometimes less than 10. It means there are few instructions which are actually creating the retiring bottleneck. And there is no need to prefetch for all the instructions all the time, because they are eventually increasing our energy consumption, right? So pretty intuitive. There's no big deal in terms of this idea. People have been working on this from last 30 years, to be honest, both industry and academia. There is nothing new in terms of this idea that, okay, let's do prefetching judiciously, and then which will actually improve our energy. But what we actually proposed is actually a metric that can be pretty simple, that can be implementable without incurring significant storage overhead. So just to give you an idea, there were proposals from Intel that actually talks about building a data dependency graph and trying to find out what are the loads which are actually creating a long dependency chain in the hardware to do all these optimizations. Okay, it sounds good for a research paper, but at the end of the day, you have to think twice before putting it inside a real processor. So what we proposed is a metric called ROB occupancy, the buffer that I talked about in the beginning, which actually contributes to the retiring bottleneck. And what we said is, anytime the processor is waiting for the data from memory, just look at how many instructions are actually waiting in the ROB. That number itself will be a good indicator of a particular instruction, whether it's critical or not. Okay, so that metric of occupancy, along with a small submetric called stall frequency, that says what fraction of time this particular instruction is actually stalling my processor, this combined metric is actually more than enough to do a pretty judicious prefetching. Okay, so what happened? I started with this ISCA paper. I said, okay, performance 45%, but that prefetcher was actually not good in terms of energy. It was consuming 50%. So now we propose this idea where it is conscious about my energy, and I'm incurring extra 2.5 kilobytes for that 5% reduction in energy. But there is a trade-off here. Whatever 2% that I have, gained based on my ISCA paper, now I'm losing just to get 5% improvement in my energy. Okay, but remember, this 2-3-5% are actually a big deal in my community. So these are actually big numbers.
So one question.
Okay, sure. Yeah, we can take it.
So are if in the case of SMTs, will the ROB entry also have instructions from the other thread, or is
Yes,
it like
it depends on the implementation, but the high level answer will be yes,
okay? So
because
then
it's a
would
shared
this
structure. It is a shared structure. So yeah.
yeah? So in that case, like would this metric be affected if we have multiple
Yes.
threads?
So it's a good question again. So this metric will be affected. So in that case, what you need is you need ROB occupancy per thread instead of the entire processor, right? So you can actually
Okay.
have a tag which says that, okay, these are the number of entries which are occupied by thread one, and based on that, you can actually make a comment about the criticality.
Thanks.
Okay. Okay, so let's move on for next 10-15 slides. Then again, I will pause. Okay. So now we have a deal that we, the performance loss of 2% that we have gained, and whether it's a big deal, well, it's actually a big deal because it takes around 2 to 3 years to get 2-3% improvement. Okay. So now the question is, can I design a prefetcher that is high performing and at the same time highly energy efficient, right? So instead of proposing two different solutions, which is solving performance in one angle, then energy in another angle, and which has conflicting trade-offs. That's the beauty of this problem. If you want to improve energy, then you have to reduce, you have to incur performance loss, right? So what I'm asking is, can I actually have the best of both the worlds, right? And that's what my next topic will be. And the answer is, why not? Well, can we design it? Yes. Let's see. So this is the work done by a PhD student from Spain. He was actually planning to come to IIT Bombay for doing research on prefetching, but he could not come, no thanks to COVID. So he will be defending his PhD thesis next week. So again, this is a remote work done during the COVID period, where I haven't met this student, but we have been working together. So the idea of this particular part of the talk will be, can we propose prefetchers which can solve both the problems like performance as well as energy? Okay. So the approach that we take, we said, okay, forget about all the high fund ideas. Let's make the problem pretty simpler. So the problem is, whenever the processor gets a request to, let's say, address X, what should I prefetch? And what should I prefetch can be termed as delta. What should I add in my address and prefetch so that in future the processor will actually generate a request for that address? Okay, pretty straightforward problem formulation. There is no big deal. To understand what I am saying, so if you look at this for loop, you will find there are like two different loads which are accessing array C and D, right? But if you look at the first array, it's actually going for C0, C1, C2, C3. So if you look at the deltas for this particular load, it will be +1, +2. Like you are actually jumping with a delta of +1, right? But for this array D, when it generates load instructions, it won't be as straightforward as we have seen for C, right? So the delta should be actually per IP, but that's what our community was not doing. They were actually trying to learn deltas for the entire program. Okay. Now there are other proposals that are already implemented in real processor that try to solve this kind of problem. But let me give you a simple example. That's what Professor Narayan Swami was asking. That okay, if I'm going for this for loop, at the top of the slide, you will see that the deltas or the difference between the addresses will be just +1. Pretty easy for any prefetcher to do anything, right? But thanks to many compiler optimizations and processor optimization, super aggressive processors, you will see that the processor is actually not executing the way you want it to execute when you wrote the program, right? It can happen that eventually the processor is executing a of 1, then a of 3, then 2, then 4, blah blah blah, right? So now if I look at my differences or the deltas or strides, these are all over the place. I don't know what exactly I should do now. The prefetcher will have no clue what exactly to be done, right? So this is similar to Mumbai traffic or Chennai traffic, like completely out of order. You can't predict about what exactly is coming, right? So what we said is, we said, okay, we will actually learn the best delta that is best for a given IP or for a given load, and we won't make it generic for the entire program. And we brought up the notion of something called aggregate of deltas that I will explain next. But we also point about something in the previous slide. If you look at, it says per IP best request time aggregate of deltas. So there's a notion of time here, and that time actually is playing a crucial role. You will see in the next few slides. So the crux here is, when you are deciding what delta to use for your prefetching, you should also have the notion of time. So I will tell you what exactly this time is. So in real systems, if you are trying to fetch data from multi-levels of cache like L2, L3, or DRAM, it's not constant. So these are the numbers on a real core, real 4-core system on a, I think Intel Haswell. So we found that that the average time it takes to get the data can vary from 22 cycles to 2098 cycles. Okay, so which means now if I have a prefetcher which can predict the delta with 100% accuracy, there is still a high probability that it won't be enough because the latency for getting the data itself is now thousands of cycles, right? So in summary, the current memory system is also out of order. It talks about many scheduling techniques, many queuing delays, memory level parallelism, and blah blah blah. In the interest of time, I won't go into the details. But we have an out of order processor, we have an out of order memory system. What else you want to design a prefetcher? Right? This is actually the problem that you want to solve. Okay, so now let's understand what exactly is the notion of time. So if you look at this slide, so these are the addresses which are generated by a processor. Let's say 2, 5, 7, 10, 12, and 15. So now if I go back from 15 and start asking when should I prefetch for address 15 so that my cache will get a hit. Okay. So if I start from, let's say, at address 12, whenever I got the address 12, I'll prefetch with, let's say, stride 3. Then whether I'll be able to mitigate this latency. Okay, so you can actually keep on asking whether I should prefetch at 10, 7, 5, or 2. Okay, so what we introduced is the notion of time to fetch this address. So if you look at this particular part of the slide, it says the time to fetch the address 15 is actually somewhere in between just before 7 if you want to amortize this latency, which means even if you have 100% accurate prefetcher and you try to prefetch at the address 7, 10, or 12 with all the intelligence that you have, you won't be able to convert a miss into a hit. And what we are arguing is you should actually prefetch before 7 so that by the time the processor requests for address 15, you will be able to get the data and put it in the cache. Okay, so these are the notion of deltas. And the notion of aggregate of deltas is you just keep on adding all the deltas that you have seen so far. So in this case, 12 to 15 is 3, then 10 to 12 is 2, right? So you add it, 3 plus 2 is 5. Then again, 7 to 10, 3. So you add 5 plus 3, 8, right? So now you have combination of many deltas. Now the question is which delta can give me the timely response? Okay, so that's the question. And that's the new question that we are trying to answer. So in one slide, this is the proposal. What we did, for every load, you actually maintain a hardware table that looks at when exactly those addresses came to the cache and what exactly the time it takes or what is the exact amount of latency it takes to get the data from memory. Okay. So if you look at this example, if I want to mitigate or if I want to convert this address 12 into a hit, I should consider the fill latency for address 12. And based on my hardware, if it says, okay, getting data for address 12 takes 50 cycles, that means I should go back and look at all the deltas that I have seen so far in the past and ask a question which delta can actually amortize this latency because this guy will take 50 cycles. Okay. So based on that, I learn the deltas, and the more I see the same same deltas, I kind of improve my learning and say that okay, this is the high probability that I can get from any of the deltas. So let's go with this particular delta, right? So that there are few heuristics that we use here and there, but the high level idea is for every load, try to understand how much time it will take, then go back in time in the temporal order and try to find out the delta that can mitigate or amortize this latency. Okay. So the insights of this paper is if you are prefetching based on this timeliness information, and if you are getting the best local delta that can cover all the misses for a given IP, then it will contribute to high global accuracy for the entire program. Okay, so this is one of the crux of the paper. And
Biswa, I had a question, Aman.
yeah, sure, go on.
Yeah. So my question is like, let's say, since we're talking about delta now, is it possible that loads that were like required at different points of time in future, they both have deltas of a form that they conflict at a certain point? That okay, at this point I must prefetch. So at for like such conflicts, like how often do these conflicts occur, and do they impact the prefetching accuracy or
Yeah. So this is a pretty subtle point. There will be conflicts. Okay, because I told that this is the out of order processor, and we are dealing with the out of order memory system. So if you look at this idea is actually learning or speculating about the latency for getting the data from memory. Okay, and it may happen that my speculation is wrong. So then there will be conflicts,
okay?
right? So again, it's not a sacrosanct prefetcher that will give you 100% accuracy again.
Okay.
Yeah.
Yeah, thanks.
Okay. So let me just move on in the interest of time. So as a package, what we propose is a prefetcher that can provide high local coverage per instruction, per load instruction, which eventually lead to high accuracy and low traffic and energy. So I'll give you numbers now. So this prefetcher, for the first time, we proposed a prefetcher which provides 90% accuracy. This was not the case with any prefetchers proposed in the last 30 years. Okay. Now the question is, what about energy? Because I defended that, okay, we need a prefetcher that can solve both performance and energy. Well, previously we used to consume 50% energy. Now it's consuming just 11%. So there is a boost of 39%. And what about performance? Well, it beats the previous best by 3.5%. So this is the global picture now. So now there are no numbers that are in red. Both are in green. So we are in a win-win situation. Okay. So again, a small message for the students. The community may think that, okay, this problem is solved. It's still not solved. I'm still working on it. You may find some better ideas, which is better than what I'm just proposing now. So keep on pushing. You never know what exactly is the limit, unless if you are working on theory where you know the limits, right? Okay, so I'll pause for a minute and then I'll talk about one, small work for next 5-10 minutes. Any questions for the part that I covered in last 20-25 minutes?
I have a non-technical question here, Vishwa,
Sure.
regarding the message. So, like, in your personal experience, how often has it happened that you came up with an idea and then you sort of realize that, okay, it won't work no matter what, and instead of pushing, you decided to like just drop the idea. So, like, how to take that call,
I think
especially.
that happens every day.
No, I mean, especially for the beginners, right? Those who are new to research, it's difficult because they do not know whether the kind of problems they are facing is normal or not, and like uh, whether they have to keep pushing or whether they should drop and like pick something else and do some other work, things like that.
Yeah, it's a tricky question. So my answer will be, you still persist, and then you never know. Eventually, you may be able to do something really different, right?
Okay.
But yeah, at the end of the day, I think you should have your gut feeling. I think your
Okay.
stomach should say more and not your brain,
Yeah.
right?
Thanks.
Okay.
Actually, Aman, my answer to the question, of course, we are the same department.
Yes.
I guess that's where talking to your advisors and maybe other people also proactively can give you a idea as to
Yes, sir.
when to chase or stop an approach.
Yeah. That's a good idea. Yes.
But maybe I'll just play the devil's advocate here. But sometimes it's okay if you don't agree with the advisor and the department. That's okay. So sometimes, not all the time.
No, no, I agree with that. I think that finally, yeah, the gut feel is important, but you should get as many opinions as possible
Yeah,
without wasting your time too much.
yeah. Sure. Yeah.
Discussions always help. True. Thank
Okay.
you.
So let me move on. I think we have 15-16 minutes. Okay, so this is the last part of the talk. We are still trying to, mitigate the bottlenecks that I started with, the memory bottleneck and the retiring bottleneck. The next part of the talk is actually about improving the performance of cache hierarchy or the memory hierarchy. And what's new about this problem? There is nothing new. The new or the quote unquote new part of this problem is the community has been solving all this memory optimization problem, not keeping operating system in mind. Okay, so let me bring you the notion of operating system and the address translation and whatnot. So when you write your programs, thanks to the notion of virtual memory, the OS and the architecture have a handshake mechanism where they say that, okay, we'll actually provide an illusion that you have all the memory in the world and you can do whatever you want, right? But in reality, there is a software data structure which is maintained by the operating system, which converts or which translates your addresses which are written, or the addresses that you see as a programmer, which are known as the virtual address, into something called physical address. Okay. Since the page table itself is really huge, people propose multi-level page table so that it won't eat up all the space in the DRAM. Now, what happens is every time you actually try to translate a virtual address into a physical address, you have to go to multiple levels of the page table, and finally you will get a physical address. Once you get the physical address, then the processor will send that address to memory saying, okay, give me the data for this address. Okay. And this entire process is done by a hardware, not by a software. So there is a page table walker, which is a finite state machine that walks this page, multiple level page tables, and finally tells you that, okay, here is the physical address for you, and then CPU will actually move on with that address. Okay. So if I want to bring in some new terms and a new microarchitecture, so memory hierarchy, so far we have been assuming multiple cores, multiple caches, but now I have put multiple TLBs. So TLBs are nothing but caches for these translations, these virtual to physical translations. Okay, and if you don't get a hit in these TLBs, the page table walker will kick in and it will go to memory or the cache to find out the translations where exactly it is. Okay. Now here is the interesting part. So if you bring both OS and the program, or the binary that you are running on your processor, for applications which are heavily memory intensive, which means they don't fit into your DRAM capacity, it may happen that on a miss for a translation at the TLB, the processor has to go to DRAM 5 times just to get a translation done. Okay. And once you get the translation, that means now you have the physical address. Then the processor will actually send that address to the memory hierarchy again to get the data. Okay. So in the worst case, it may happen that a simple A of I that you have written in your program can lead to 6 DRAM accesses. So if I take the estimate of 100 cycles per DRAM, so it will take 600 cycles just to get one A of I, right? So few terms that I will introduce at a pretty high level. So we introduced a notion of called replay load. It's not a textbook definition. So the definition of replay load is whenever you get a miss in the TLB, and after that you do the page table walk, and finally you get the translation. And then after that, when you send the physical address to get the data, that load address is a replay load. But if you get a hit in one of the TLBs, let's say L1D TLB or STLB, then the corresponding load request for that translation is a non-replay load. Okay. And with that, we started experimenting with most of the memory intensive workloads. So what we have found here is, if you're getting a TLB miss, it's not a big deal. If you look at the average number, it takes around less than 50 cycles. But the problem here is the replay load. Replay loads are the loads which are coming after the TLB miss. So you miss in the TLB, you do the page table translation, and then after that, you go for the actual data request. So what's the message here? The message here is, if you're getting a miss in the TLB, that means the OS page is already cold. It's not getting accessed frequently. If the OS page is cold, the corresponding data that is residing in that OS page will be even cooler. That's why it's not there in the entire memory hierarchy. That's why this latency is actually close to 200. Okay. So now with this motivation, we looked at the state of the art cache management techniques. And if you look at this plot, the y-axis shows what is the miss rate or the misses that you are seeing at the L3 cache. And you will see that all the cache management policies have no impact whatsoever, right? More or less, they are the same. Then I asked, okay, whether prefetchers will work. Come on, prefetchers won't work because we don't have the translation done yet. Once we get the translation, then only we'll get an address, then only I can do prefetching, right? So even prefetcher, they can do here and there a few things, but even they can't help. Okay. So now what's the solution? The solution is pretty, intuitive. Anyone can come up with the solution. The solution was I should make sure that the translation entries are actually cached in my cache hierarchy L1, L2, L3 for a longer duration. Okay, so we came up with a simple technique that makes sure that 99% of the translation request coming from a page table walker will actually give you a hit in one of the cache level and definitely by L3. Okay, so this is a big result because now it makes sure that you are not going to DRAM for your page table walk. Okay, once it is done, we proposed a prefetcher, but this prefetcher is a completely different prefetcher. So I will take a minute or two here. So here the idea is, if you look at the top of the slide, the baseline, here it says you get a TLB miss, then you go to L1, L2, and let's say finally you got a translation hit in the LLC thanks to our optimization, right? But once you get a hit in the LLC for translation, after that you again send the replay load that will get a miss in L1, L2, and L3, and finally you get it in DRAM. You will send it to processor through 3 levels of cache. What we proposed is the moment I get a translation at my L3 cache, I should trigger a prefetch request for the final physical address that the page table walker was walking. So what's the benefit? The time at which I get a hit at the LLC, if you look at the option B here, I am getting a hit for virtual to physical address. The moment I get a hit, I initiate a prefetch request for the physical address. And in the meantime, processor will actually send the request which will come through the normal path, L1, L2, L3. But since I have already generated a prefetch request, the data has now come to LLC. So now when the translation is done, my data is also getting a hit in the LLC. It's not going to DRAM. Okay. And remember, this prefetcher is 100% accurate because it's not speculating. It's just doing a preloading. I know that this is the address that the processor will request. I'll just load it as soon as possible. Okay. So this is the idea. And if you look at it, this is actually pure common sense. There is no big deal out of these two ideas. Okay. And finally, what happened? We actually reduced the stalls created by these address translations. These are the numbers that you can see: 28% for translation and 18% for replay loads, which lead to extra 5% improvement, 4.8% performance improvement. Okay, and this is the summary here. So this idea doesn't demand extra hardware. Okay, the only thing that we need is OS should communicate to the cache hierarchy through the page table walker that this is the last level I'm actually walking in my page table. Once you are done, then you can take that address as the physical address and move on with the prefetching. Okay. So this is the summary of what I have talked so far. I'll actually try to wrap up now in the interest of time. So if you look at the kind of problems that we have solved in the last 3-4 years, yeah, these are difficult problems, but interesting insights. And finally, it can be rewarding, right? That's why people are actually talking about these small ideas. So when you get so much GAN, sometimes it's better to pause and think about it, whether you should listen to all the GAN or just follow your gut feeling. Okay, so what next? Maybe some other talk after a few years where I will talk about security side of microarchitecture, or security and performance both, hopefully through students at IITB, and we are on it. Okay, so this is a group which is led by me, pretty new group. So if you're at IIT Madras and then you love you're still loving dosa and you want to explore vada pav along with dosa, then do consider joining. Okay, so in a nutshell, this will be my message, keeping some of the interesting problems that students can explore. Is that you start with the impossible, you know that it's impossible, but that will actually push you to think about some possibilities. Okay, and my take from last 5 years is, if you know the problem well, then you know the solution well too. So most of the time we struggle to find out the solution because we don't know the problem well. So spend months and years to understand the problem, and suddenly one fine day you will get the solution. Okay, but those initial years are actually the 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 days where you're actually thinking about the solutions. Okay, so I'm kind of a big fan of cricket, so I also try to pitch research, microarchitecture research, architecture in the form of cricket, especially test match cricket. So if you look at this quote applies for research also. You can just replace play life like a cricket match into play research like a cricket match, where you have to just keep on doing your homework every day. Okay, it's not like you have to hit sixes every ball like IPL matches. Okay, and but you have to look for that one delivery where you can actually hit as hard as you can, right? And that will actually make some impact in the community. Okay, so with that, thanks to all the students who actually contributed these works, and thanks to these research labs who are funding me unconditionally, and because all the works are actually done remotely during COVID, thanks to my small family also. And last but not the least, thanks to IITM for not kicking me out during my MS program. So thanks again.
Thanks a lot, Biswa, for very entertaining and interesting talk.
We can take questions, maybe?
Yeah. So if there are any questions from the audience.
No questions.
Okay, I have a question.
Sure.
You should go to that slide where you have the cat hanging in.
Okay. Persisting.
Yeah.
67 or something before that. Oops.
I think you should change the background image. It gives the feeling that it is a jail.
Okay.
In some movies, I mean, you get to see this gives the feeling of a jail. So
Got
I
it.
don't.
Okay.
No, just I mean, it's a light comment. So
Yeah,
just,
sure. Yeah, I didn't pay attention to it.
okay, sorry, yeah.
Yeah, it looks like our Subramaniam Shankar block.
No.
This is now accentuating the joke more.
And all our research labs are.
No, so okay, so my intention was to show the reality, okay, instead of showing something.
Okay, this is confusing.
Right. So yeah.
Okay, let's not talk more because the recording is on.
Oh, okay.
Yeah. Any.
I have a technical question, Bishwa.
Sure.
So, is the following idea meaningful at all? That I mean, if there is enough data for the prefetchers, then probably the prefetcher itself can be designed by say machine learning approaches.
Yeah.
But then you really don't have the logs for the access patterns, right? I mean, or is there? I mean, is there an interesting way of getting it?
Yeah, the community has already jumped into it. So you will find papers at top forums making a case for the usage of machine learning and AI for hardware prefetching. And the state of the art is you need GBs of data to do, good enough prefetching. This is the state of the art at this moment. But having said that, as an intellectual exercise, yes, it makes sense.
But you also need to get the trace, right? I mean, for that you need hardware
Yeah,
features. Which
you have to do offline analysis. You will assume that this is not a
Ah,
real problem. I will take the trace and then I will take it as a machine learning problem.
no, my question is just to get the trace. Would that be done by hardware, or is there profiling tools which can tell you
There
what are
are
the
tools. Yeah, there are profiling tools that can give you the trace, and then you can feed that trace into your ML model.
Any final questions from anyone?
Yes, I should change this slide, otherwise I won't get any questions.
All right. So if there are no further questions, thanks a lot, Biswa, for this wonderful talk, and we look forward to interacting with you further.
Sure, same here. So
All right. Thank you, everyone, for joining.
Thanks.
Thank you, Ritesh.
Bye.
Thank you, Bishwa. Bye.
Bye.
Thank you. Bye.
Thanks, Viswa.